Hi class, and welcome to Chapter 2, Section 1. Chapter 2 deals a lot with the properties of matter. Specifically, Sections 1 and 2 kind of delve more into those properties. So let's talk a little bit about the properties of matter. When we can describe matter, a lot of things can go into how we describe matter. And again, matter is anything that has mass and takes up space. So we can describe matter by the texture, what it does, the actions, the shape, the mass, the amount, the volume of space it takes up, the density, the size, and the color. So lots of different ways to describe matter. And properties that describe matter can fall into two categories: extensive properties or intensive properties. So the extensive properties of matter will depend on the amount of matter of a particular substance. So for example, of an extensive property would be the mass, the amount of matter that that object contains. The volume is an example of an extensive property of matter, the measure of the amount of space an object occupies. The intensive properties of matter do not depend on the amount of the matter itself, but more on the type of matter. An example of an intensive property is odor, or color, or the absorbency. Those are all examples of intensive properties. And then to identify the substance matter that has a uniform and definite composition is then called a substance. And every sample of a given substance has identical intensive properties because every sample has to have the same composition. The physical properties of matter. So a physical property of matter is a quality or a condition of a substance that can be observed or measured without actually changing the substance composition. So a physical property, when you're working through your lab or when you're thinking about substances and their physical properties, think of a quality or a condition that you can see or you can measure without actually changing the composition of that substance. So for example, how hard something is, the color of something, the conductivity, can it conduct electricity, and the malleability, meaning can it bend, or the melting point or boiling point. These are all examples of physical properties of matter. These are all qualities or conditions of a substance that can be observed or measured without actually changing anything about the substance's composition. Understanding those physical properties is really important in this section. More about the physical properties, these can be very useful to chemists and other scientists to help them identify what they're studying. Substances that are similar will have at least one physical property that will make it different. And now let's go through the different states of matter. So when we're talking about matter, we can have solids, which have a definite shape that does not depend on the shape of its container. That just means that if I have a container, let's say my water bottle, and I put solid rocks inside, the rocks are solid. They will not change shape depending on the container that I put them in. So a rock is an example of a solid. It does not depend on the shape of its container. It has solids will have definite volume, and the particles in solids are packed very close together in a very orderly arrangement, and that's what makes them solid. They are incompressible, meaning you can't make them smaller in any way. They are a solid. But they can expand slightly when heated, and that's because all of the nicely compacted particles start to move a little bit in solids when they're heated. And that slight movement of the particles when there's an increase in temperature causes a slight expansion of the solid. There is vibrational motion of those tightly compacted particles when they're heated. but there's very low kinetic energy, meaning they're not moving around a lot. They're just slightly moving because they're very compacted tightly together. All of these properties are what define a solid. Now let's go through liquids. Liquids have an indefinite shape, but they will take the shape of the container. So think of your water or your coffee or your sports drink. When you put it in the water bottle, it will take the shape of the container that it's in. So they have an indefinite shape, but when they're in a container, they will have a definite volume. The particles in liquids are close together, but they're far enough apart so that they can slide past each other. And that's what makes liquids, gives them an indefinite shape. The arrangement of particles is not rigid or orderly the way it was in solids, and there's a flowing motion to the particles in liquids. They are almost incompressible, meaning you can't compress them in on themselves. And they also tend to expand slightly when heated because, again, heat causes the particles in liquids to move a little bit, and that causes them to expand. So there's a little bit more of a moderate kinetic energy, meaning the particles can move a little bit more than in the solids when heated. We always use the symbol as a lowercase l to signify a liquid. Moving on then to gases. Gases have an indefinite shape. They will take the shape of the container, and they have an indefinite volume because gases have particles that can move all over the place, and gases will always expand to fill any container. And to give you an example of this, spray some perfume or body spray or something that smells nice in one corner of your bedroom. That spray is an example of a gas, and eventually those gas particles, if you spray enough, will fill up the entire room and you'll begin to smell it. So that's why we say gases have an indefinite shape. They take the shape of any container they're in, for example, perfume in a bedroom, or they also have an indefinite volume because they can expand to fill any container almost indefinitely as long as you have gas particles present. Particles are very far apart. They're easily compressed to a smaller volume. So that means that you can take another gas like oxygen or nitrogen, you can take those gas particles and compress them into a smaller volume and into a smaller container. Gas particles move in a constant, rapid, random, and straight line motion. And because of that, they have very high kinetic energy or very high motion. And we use the lowercase g as the symbol for gases. The term gas will refer to the state of matter at room temperature. If we use the term vapor, that refers to a solid or a liquid at room temperature, but when heated actually becomes a gas or vapor. Let's talk about plasma. Plasma has a very high energy state that can conduct electricity. Plasma is composed of a mixture of ions, electrons, and neutral atoms, and it usually includes the group 1 elements in the periodic table that usually form what we call plasmas. And we'll talk about how we arrange our periodic table, but it's group 1, that first column in the periodic table, that has elements that usually form plasmas. They exist at very high temperatures. Let's talk about the Bose-Einstein condensates. So let's talk a little bit about some of these states of matter and the properties of matter. These condensates describe how matter waves will overlap and a little bit of movement of these particles of matter. These emerged in 1995. They're like a superfluid, and they exist at almost 0 degrees Kelvin. Particles will behave like waves in a situation that we call the giant matter wave, and the display is very unique and gives it very bizarre characteristics. So we have very high temperature, we have what we see kind of look like particles moving like billiard balls, kind of bouncing off each other. At very low temperature, the particles are moving like little wave packets. And then with the Bose-Einstein condensation, we see how these matter waves will overlap until we get to a temperature of 0 degrees Kelvin, where you just kind of have a giant matter wave. I won't ask you too many questions about this, but I wanted to go through it a little bit in lecture in case you see it in your textbook. More about physical changes. During a physical change, and you'll be looking at your lab activity this week on this, some properties of the material will change, but the overall composition of the material does not change. So that would still be an example of a physical change. There will be no new substance created. So when you're thinking of how to determine between a physical and between a chemical change, in a physical change, some properties of the material may change, but the overall composition of the material will not change, and there will never be any new substances created in a physical change. More about physical changes, words to look for when you're trying to determine, if something is a physical or a chemical change. If something is boiling or freezing or melting or breaking or splitting, grinding, cutting, or crushing, those would all be examples of physical changes because the overall composition of the substance is not changing and there's nothing new being formed. If something is boiling, for example, and there's a new substance being formed, that would be a chemical change. But in general, if you're just boiling a substance, nothing's formed, freezing it, melting it, breaking, splitting, grinding, changing the shape of it, but no new substances are being formed, that would still be examples of all physical changes. Physical changes can be classified as reversible, meaning that a part of matter can go through a phase. So some sort of matter or substance can go from a solid to a liquid and then back again from a liquid to a solid. That would still be an example of a physical change because the substance is not changing composition. For example, if you take water, you can boil water, you can freeze it, it can evaporate, but those are all physical changes. Nothing new is being formed, and the overall substance is not changing. However, some physical changes can be irreversible when you break something into pieces. So if you completely shatter a bowl or, break, splinter a piece of wood, a physical change can be irreversible where something can completely break or shatter or splint or grind or become crushed. And it's still a physical change because nothing new was formed. You just now have a million pieces of glass on the floor. There was no new substance being formed. So that is all examples of physical changes. So that takes us through chapter 2, section 1, and take a look for our next video for chapter 2, section 2. Thank you for listening, guys.